Hello, this is the question 1 of homework 10, and the question is find some definitions and simple properties of these processes. So we can first look at the Poisson process. So we know that the Poisson process is like the probability of number of calls received in T hours equals K. So which means it is like this. So it is a number and in T time equals K. So it is have a probability which is E minus lambda times and lambda T K times over K. So we can have this. So this is the definition of Poisson process. And it has some properties, which means uh, the expectation, which is eta t, is equals to lambda t, and the autocorrelation, which is r t2 t1 t2, is equals to lambda square t1 t2 plus lambda minimum t1 t2, and the uh, second moment, which is e x squared t, it is equal to lambda t squared plus lambda t, and epsilon square is equal to lambda t. And we know that, so it is the eta is equal to lambda t, which means the lambda is um, so the lambda is the average in the t time, and it goes larger when t goes larger. So this is the property of the Poisson process. And another property is that when there are non-overlapping intervals, which means it's a t, and there is t1, t2, t3, t4. There are two non-overlapping intervals. So if there are two non-overlapping intervals, these two intervals are independent of each other. So this is the Poisson process. And the second is Poisson increment. So which is Poisson increment? Poisson increment is like this. It is yt equals x t plus epsilon minus xt over epsilon. So we can find some property of this, which first one is 1 yt equals n over epsilon. It is equals to e minus lambda epsilon n over n. And the average of it is lambda. It's a constant. And the autocorrelation is r t1 t2. It is equal to lambda square when the in the inter the distance is larger or equal than epsilon, and it is equal to lambda square plus lambda over epsilon minus lambda t1 minus t2 over epsilon square when the distance less than epsilon. So the Poisson increment process is just the increment of the Poisson process. So when we can see that when the uh, 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 what we can see that the eta is lambda, so it is independent of the time. So this is the Poisson increment. And the third one is Poisson impulse. Poisson impulse is defined by Zt equals dxt dt, which means it is equals to 1 epsilon lambda goes to 0, the Poisson increment. And the average is equals to lambda. And the autocorrelation T1, T2 is equals to lambda square plus lambda delta T1 minus T2. So this is the Poisson impulse. It's a derivation of the Poisson process. And number 4, which is semi-random telegraph signal, which is if uh, we have one k, which means the k is the point over the axis, and we have the k is the number of points over across the axis, and which is the k is the probability of k is equal to e minus lambda t and lambda t square k over k, and 1 x0 is equals to 1, which means 1 x 1 t equals 0, the value is 1, and 1 t not equals 0, it is equals to 1, 1 k is even in 0 and t, and 1 it is minus 1, 1k is odd in 0 and t. So this is the definition of semi-random telegraph signal. And we can get that the average eta t is e minus 2 lambda t, and the autocorrelation is t1, t2 equals e minus 2 lambda t2 minus t1. So because it is semi-random telegraph signal, so the x0 must equals to 1. And if the distance of T1 and T2 are very large, the autocorrelation will go to very small. So there is very less correlated. So this is the semi-random telegraph signal. And the fifth is random. The random telegraph signal. The random telegraph signal which is similar to the semi-random telegraph signal, but the x0 can be equals to 1 or minus 1. So the random telegraph signal is like in this form, which is yt equals alpha xt, which alpha is equally equals 1 or minus 1. They are both 1 or 2. So this is the random type of signal. And we can know that because it is equally 1 or minus 1, 1x equals 1t equals 0. So the eta it is 0. And the autocorrelation R T1, T2 is equal to E minus 2 lambda. And this is T1 minus T2. And it is also equals to the autocovariance, which is C T1, T2. So they are the same. And so this is similar to the semi-random telegraph signal. And six is random walk. Which is random walk? Random walk is that x and t equals ks minus n minus k s. It is equals to 2k minus n s. So S is if we get a head, we what value we can get, and K is the number of head, and N minus K is number of tail. So it is just like this. So which is if we got head, we get little s, and if we get head, we got 2s, and if we get a tail, it goes to minus s. So this is a random walk. And so because it is randomly tail and head and tail, and the probability is the same, so we can know that the pxt equals to rs is equals to c to this sorry cn from this, and this is to this, which means 1t between nt and n plus 1t. So the mean value is 0 because we have the same property of head and tail. And autocorrelation is RT1, T2. It is equal to the mean and n s squared. So the m and n is in this. So T1 equals mt and T2 equals nt. And you can also get it is the same. It is equal to autocovariance of T1, T2. So the final one, which is Werner process. This process is when we have a random walk, and when the random walk we get when t equals 0, this t equals 0, and s squared over t goes to a, and n goes to infinity when we have a random walk. So this is the linear process. And now we can get the property of this is that we have the density function, which is FWT equals 2 pi a t, and is e minus w squared 2 a t. And the average of this is equals 0. And the autocorrelation T1, T2 is equals to the autocovariance T1, T2, which is equals to minimum of T1, T2 multiply A. So this is the linear process, and it's similar to the random walk, but it goes to more like a long time and in a short time interval random walk signal. So this is the linear process.